All right, hi everyone. Thank you for tuning in. Welcome to the 37th online Spintronics seminar. This is Feng from University of Denver. It's my great pleasure to introduce our speaker today. Professor Feng received his PhD in Applied and Engineering Physics from Cornell University in 2014. His graduate studies focused on the giant spin Hall effect in transition metals and spin orbit torques in magnetic heterostructures. After graduating from Cornell, he worked at MIT as a postdoctoral research associate in the Department of Material Science and Engineering. He's currently a faculty member in the Department of Material Science and Engineering at National Taiwan University. So without further ado, Feng, please take it from here.
Okay. Thanks, Professor Fan, for his introduction. Let me share the slide first. So I hope everyone can see the slides. And the topic of my talk today will be probing spin orbital switching through unidirectional magnetoresistance. Although it will be not restricted to just unidirectional magnetoresistance, as you will see later, but this is the title. And my name again is Feng. I'm currently an associate professor at the Department of Material Science and Engineering at the National Taiwan University. And this work, I'm going to show you some results taken from the devices made by a team at the Electronic and Optoelectronic System Research Laboratories at the Industrial Technology Research Institute, or ITRI for short. So if you have a question or later on, if you have more, you want more information regarding the talk I'm going to talk about today, you can refer to this work that we just published earlier this year by my student Yenting Liu on physical review applied. And before going into the research part, I want to show you briefly like how we have this kind of collaboration between National Taiwan University and the Industrial Technology Research Institute. So we have several Spintronics related research group at National Taiwan University, including my own group, and also a different group from the physics department led by Professor Suyuan Huang, who will give a talk in October 6th, I believe. He will probably talk about research on the spin feedback effect or thermal related topics. And for my group, I'm focusing on the study of spin orbital and mainly about spin orbital switching, either from classical like transition metal based material systems or topological insulator based systems or even non-epitaxial chalcogenized systems. And our collaboration with ITRI started when I first joined NTU back in 2016. And you might not have not heard of ITRI, but you probably have heard of its spin-offs back in 1980s. One of them is the probably largest chip makers in the world, the TSMC, and the other one is called the UMC, also a major chip makers. The reason why we collaborate with ITRI is because they also wanted to develop SOT and RAM on their 8-inch fab facility. So at that time, we started to want to figure out if there's any better way to, for instance, characterize spin orbit torque in a faster way. Because typically, to make a full like SOT and RAM on their 8-inch wafers, it will take starting from the thin film deposition to the patterning and the etching processes and to the final device. It will take probably 2 to 3 months. So we wanted to see if there's any possibility that we can see some early results before making those films into devices. So the options for SOT characterization, this is the sort of the map I show them when we started to discuss about collaboration is that if you want to do like the systems with ferromagnetic layer having perpendicular anisotropy, which is the PMA shown here, then you will go to the path, to the above path. And if you want to characterize SOT from those films with ferromagnetic layer being in-plane magnetized, then you have to go from this path. And the first question that we encounter is that whether or not you can pattern your films into nanopillars. So if you can make those films into like 3-terminal magnetic tunnel junctions, and you can measure TMR, tunneling magnetoresistance, then you can just directly pattern them into nano-sized devices and then measure the spin orbital switching. But this is typically hard for even for a fab like a research institute with well-established fab facility. And it's also very difficult for like university labs. So that's the reason why we sometimes want to go for other types of characterization methods. So if you cannot make nano-sized devices, then you probably can make, say, micron-sized devices using standard photolithography to make them into whole bars. So if you can do that, then if you can apply both in-plane and out-of-plane field, then you can use the hysteresis loop shift measurement. This is by measuring the anomalous Hall voltage, but at the same time, you apply an in-plane field. And so if you can do that, you can characterize SOT efficiency. But if you cannot apply the in-plane field, out-of-plane field at the same time, but you can apply a one-direction magnetic field, you can still use the standard like harmonic voltage measurements. I believe that if you're in the field of spin orbit torque, you probably, or one of your students have used this kind of techniques to characterize SOT, because all you need is, like say, an AC signal source, and you can probe the first and the second harmonic voltages from your whole bar device. Then through some simple analysis, you can extract the SOT efficiency. So that's the reason why this technique is very popular. However, if the case is that you're dealing with in-plane magnetized ferromagnetic layer, the situation will get more complicated. Even if you can pattern your films into micron-sized devices, you probably cannot directly probe current-induced SOT switching. This is because in micron-sized devices, the magnetization switching may be more complicated, and it has maybe domain-wide motion involved. So to work on SOT characterization in micron-sized devices, people typically will use, for instance, spin torque FMR measurements. This is also a very popular technique for people who wants to work on samples that does not have PMA. And if you cannot pattern your films into micron-sized devices, all you have is bare like films, you can still do like spin pumping measurement. So that's the reason why I call this fab-free. So you'll see that several methods are fab-light or fab-free, but in order to get very, very good like SOT switching data, you probably have to go through this fab-intensive process. So today, what I'm going to show you is that you can probe SOT switching even if your film is having in-plane like a magnetic anisotropy. And this is probed through the spin Hall effective field and also the unidirectional spin Hall magnetoresistance. So if you're interested in all these different techniques, you can refer to these, for instance, for SOT switching in the nano-sized devices, you can refer to the papers by Maron and Luqiao Liu. And also for harmonic measurements, you can go for this very good paper by Kim and co-workers. And for the work that I'm going to show you today, as I mentioned earlier, it's already published in Physical Review Apply earlier this year. In fact, when ITRI proposed this collaboration, actually over here, I suggested two different approaches to have this fast track SOT characterization for in-plane magnetized samples. So first of all, for these samples that we're going to work on, it has typically this kind of bilayer structure. Okay, so the heavy metal layer is the layer that generates this large spin Hall effect or large spin orbit coupling. It can be replaced by, for instance, topological insulator or other types of emergent materials. Okay, but the most important thing is that we're dealing with in-plane magnetized ferromagnetic layers. And I assume that you will have the capability to pattern these films into micron-sized whole bar devices for standard, for instance, transport measurements, to measure magnetic resistance, to measure, for instance, Hall voltage. And the switching that we're going to focus on will be the so-called X-type, the Y-type. The Y-type switching, for Y-type switching, you apply current along the X direction, as shown here. And then the magnetization will be switched along the Y direction. So imagine that if you have your ferromagnetic layer over here on top of the SOT material or the heavy metal layer, and when you apply current along X direction, the spin torque will switch the magnetization in between this positive Y and negative Y directions. So in the past, if you just measure the magnetoresistance or the AMR, due to the symmetry, the magnetization pointing along positive Y or negative Y direction will not give you any resistance difference. So in order to probe the switching event, you have to think about some other approaches. And this method that I show here was proposed by the team at Hitachi Global Storage, a Western digital company, back in 2016, led by Jordan Katine. And the approach that they propose is called the differential planar Hall effect. So in fact, they are measuring the planar Hall voltage or the planar Hall resistance of this Hall bar device. But as you can see, when you scan the magnetic field along different angles, the Hall resistance will behave just like what you expected. But in order to see the difference or in terms of Hall resistance between the positive Y and negative Y direction, which will be corresponding to the 90-degree and let's say the minus 90-degree on this charge, you have to apply an extra in-plane field along X direction. So for this type of measurement, you have to apply an additional in-plane field along X in order to break the symmetry. For instance, if your magnetization is pointing along minus Y direction, and when you apply a positive X direction field, the Hall resistance will be increased. However, if your magnetization is pointing along positive Y direction, then the Hall resistance will be decreased. So in this case, you apply an in-plane field and you break the symmetry such that you can tell the difference between the positive Y and negative Y states. So over here, they show their representative like a switching or the, like say, the probing protocol and their measurement results. So this is the switching current they apply to send into this Hall bar device along X direction to switch this nanopillar. And for each step, they have to apply a positive and negative magnetic field along X direction, and then measure the difference in terms of Hall resistance, such that they can see this kind of difference in terms of Hall resistance by sweeping the magnetic field along Y. So the measurement protocol is actually quite complicated because you need to apply in-plane field along Y direction to switch the magnetization, and at the same time you have to apply a positive and negative X direction field. However, when you switch the magnetization using current, it might be a little bit easier because all you need is to change the in-plane field along X direction and then apply the current pulses as what is shown here. And you can see this kind of very clean switching curves. And from that, they estimated the SOT efficiency from this type of device. And I believe that they use platinum as their SOT source, or the heavy metal layer. So we did try and use this kind of approach. We proposed this to E-Tree, but they realized that it's very hard to get integrated into their, for instance, automatic testing equipment. So we decided to use a different approach, MOC measurement. So MOC measurement has been used in many recent papers. For instance, in 2017 and in 2019, both from the Hyung-Soo Young's group at the National University of Singapore. They used, for instance, tungsten telluride, a permanent bilayer structure, and then they sent a current through this bilayer structure, and they used longitudinal MOC to see the magnetization switching of the permanent layer. And you can see a very clear contrast such that they can verify this switching event. And also they did that earlier in the bismuth selenide permanent bilayer structure as well. So for these material systems, you'll see that if you want to grow perpendicular layer, magnetized layer, ferromagnetic layer onto it, it will be very difficult. So in this case, they have to resort to this in-plane magnetized ferromagnetic layer. And probing the magnetization switching electrically is also quite challenging. So it seems that the easiest approach is to use an optical approach. But again, this proposition has been declined by E-Tree because they want, again, electrical testing protocol. So the last choice that we resort to is actually the unidirectional spin-hole magnetoresistance. And this effect was actually proposed by Jean Avchy in 2015. He was also one of the speakers in the previous seminar talk in this series. And for this kind of measurement, again, you use this kind of bilayer structure. But the measurement itself is very simple. If you apply a positive current flow and the spin will be accumulated. The spin will be accumulated at the top surface of the platinum-cobalt interface. And when you apply a negative, let's say, current along opposite direction, the spin accumulated at this surface will be pointing along a different direction. So by changing the current direction, you will see different kinds of spin accumulation at the interface. So that will cause a minute change in terms of the longitudinal resistance that you measure. And in this case, in the paper published in Nature Physics back in 2015, they used a lock-in technique. They utilized the second harmonic resistance by applying current, this AC current through the platinum cobalt and also tantalum cobalt bilayer structures. So the reason why they use these type of samples is because we know that tantalum and platinum, they have opposite spin hole angles. So you will see opposite trends in terms of this shift of the second harmonic resistance because platinum and tantalum, they have different kinds of spin accumulation when you apply the same direction of current. They also observed that this kind of unidirectional magnetoresistance is linearly proportional to the current that you apply into this bilayer structure. And the tantalum and the platinum case indeed have opposite trends. And from the thickness dependence data, they can extract, for instance, the spin hole angle and also like the spin diffusion length in the tantalum and the platinum layers. So when we read this paper several years ago, we realized that this should be a very promising readout process or readout protocol if we can extract this kind of signal in different types of heavy metal like ferromagnetic layer bilayer structure. So what we did back in the 2018 was by using tungsten as the spin hole material, because we know that tungsten has one of the largest spin hole angles or spin hole ratios in transition metals, pure transition metals. So we use this kind of tungsten cobalt ion boron bilayer structures, and we cap this device with 2 nanometers of tantalum, and will get naturally oxidized. And we patterned these films into 5 micron wide whole bar devices. And the measurement protocol is actually the same. We scan the in-plane field along y direction, and since the cobalt-boron layer is in-plane magnetized, the magnetization should be swept between like positive y and negative y directions. And at the same time, we measure the longitudinal resistance. Only in this case, like we use a DC current instead of like an AC current was used by Dr. Avicii. So over here, I show a very a representative the current AMR result measured by from this device. So 2 features can be observed. First of all, indeed, we can see this kind of offset, which corresponds to the unidirectional spin-hole magnetoresistance. So by changing the field direction, we indeed see this kind of offset. And that offset can also be created by changing the current direction. And more interestingly, we also found there's a shift corresponds to the current-induced effective field. And when you increase the current, the AMR loop will be shifted more significantly. And this shift in terms of magnetic field is linearly proportional to the current that you apply. And this USMR is also linearly proportional to the current that you apply, similar to, which is the same as reported by Dr. Avicii. So we summarize this kind of linear trend over here. You see that for tungsten case, the slope when you apply when you apply the current and you record the center of the AMR loop, this shift is linear, and the slope is positive. And for the platinum case, if we replace the heavy metal to platinum, we do see that the slope has become negative. So we believe that this shift of the AMR loop or this effective field is originated from the spin-orbit coupling in the platinum or the tungsten layer. And the USMR is also having the same linear trend as I mentioned earlier. And if you see the platinum case, is also having a negative trend, a negative slope. And the magnitude of the USMR in the platinum case is also smaller, which is consistent with the result from Dr. Avicii. So we also do like thickness dependent measurement on this kind of on these 2 effects. So we found that this effective field and this USMR per current density have a very similar 1/T trend as shown over here. So this is from the tungsten cobalt boron sample with different cobalt boron thicknesses. And as you can see, the effect is actually very small if your cobalt boron thickness is, say, greater than like 3 nanometers. And only when the thickness of cobalt boron layer is less than 3, you start to see this significant enhancement of both USMR and also this current-induced effective field along y direction. In fact, actually, Professor Feng worked on this in the very early days of this, in the early development of spin orbit torque. Back in 2014, he already observed this kind of a trend in the platinum cobalt boron system. And only when the cobalt boron layer is thin, say thinner than 1.5 nanometer, we do see this kind of spin orbit field. So over here, I coined this just effective field or the spin hole field, but it's actually, I believe, is similar to what Professor Feng proposed back in 2014. So since we can measure this kind of shifts and also having the USMR, we decided to use this kind of AMR, modulated AMR to probe the SOT switching. So we use the sensing current of 1 milliamp, and we'll see that if you apply 1 milliamp of sensing current, the whole AMR loop will be shifted from the original position to slightly to the right. Okay, so this is simplified from the figure or the data I showed earlier in this slide. So when you apply such sensing current, the whole AMR loop will be shifted to the right. So even if the original AMR resistance for magnetization pointing along positive Y or negative Y directions are having the same value, once you have a positive sensing current, the AMR that you measure for these two states will be different. And in fact, that's exactly what we observed. So this is the measurement protocol. So all these measurements are done with applying DC current pulses. And the right current will be, stepped, like say, every 0.2 or 0.5 milliamps, and then we can sweep change the current amplitudes from negative to positive and back to negative. So we start from this point, and then we measure the resistance, and we do see this kind of switch in terms of the magnetization. And we know that when the magnetization is pointing along, let's say, negative Y direction, it will have a higher resistance, lower resistance. And if it's pointing along positive Y direction, it should have a higher resistance. So this is a proof or an evidence showing that by measuring this AMR loop, we can, or longitudinal AMR, we can directly see this kind of switching. And the same thing will happen when you apply a sensing current of minus 1 milliamp. So the only difference here is that we change the sensing current to minus 1 milliamp. And of course, the AMR loop will be shifted towards an opposite direction. So the situation will be exactly the opposite. So you'll see that the switching loop is opposite to what you saw in the previous slide. So this is also as expected. So a protocol that we established is that for the sensing current, we apply, for each step, we apply both positive and negative currents. And then we subtract the resistance that we measure, which means that we subtract this loop with this loop. And then we can get a larger signal in terms of delta R. So in fact, this is identical if you consider the harmonic measurement as just let the lock-in amplifier do the subtraction for you. This is exactly the same as the lock-in or the lock-in result or the R2 omega result. So we can see that when the field is around 0 Oersted, which means that the magnetization is around the 0 point and it's either pointing to the negative or positive Y direction, there is a very obvious delta R. And that value will be consistent with what the step that you record, that you will observe by sending current pulses into the device. So the current-induced switching is indeed a full switching result. We also did this kind of measurement on platinum-based devices, and we do see this kind of switching as well. But you'll see that the switching current that you need will be larger, and also the signal-to-noise ratio is also not as good as those from the tungsten device, because as mentioned earlier, platinum devices have lower USMR response. You might also wonder why this polarity of the switching loop is the same as the tungsten device. This is because, of course, the spin orbital switching polarity will be opposite to the tungsten device, but at the same time, our USMR signal is also opposite to the tungsten device. So if you take these two into account, you'll see that this kind of polarity is as expected. We also did this kind of measurement on different kinds of cobalt boron thickness, for instance, 2.5 nanometers, and we also can see very clean switching results. And from this kind of switching measurement, we can actually extract a lot of more information than just by doing the characterization or the typical like let's say, harmonic voltage measurements, either for PMA or in-plane samples. From the switching measurement, you can extract the thermal stability by changing the pulse width. So we can actually do this by changing the temperature, but the data that I'm going to show you today is by changing the pulse width. So by changing the pulse width, you will see that if you plot the pulse width over this intrinsic relaxation time, maybe I think it's 1 nanosecond in the log plot, you'll see this very linear trend. And from the fitting to thermal assisted switching model, you can extract the zero thermal critical switching current density from this device, for this device, and also the thermal stability. And because this is a micron-sized sample, so you can see that the thermal stability that you extract can be pretty large, because you can imagine it's very hard to switch this large magnetization. And also, more importantly, from these two data, or these two estimated results, we can estimate the switching efficiency, or the spin-torque switching efficiency. Because over here, at least for E3, they wanted to know not only the critical switching current or the critical switching current density, but also the ratio between thermal stability to the critical switching current. Because this is sort of the figure of merit to determine whether or not this device or this heterostructure is going to be useful for the real memory application. Although over here we're dealing with micron size, but I think eventually we want to, again, shrink the size of the pillars, or at least pattern those ferromagnetic layers into nano pillars and do the same thing. But that's for the future work. Over here, we're just trying to demonstrate a proof of concept. So we can see that this is the result from tungsten cobalt boron samples with different cobalt boron thicknesses. All of them are having this switching efficiency around 2 times 10 to the minus 2 microamp inverse. So if you look into some old literatures, we're focused on STT switching in the magnetic tunnel junctions, or nano-sized magnetic tunnel junctions. You'll see that this number is actually quite much larger than those values extracted from nano-sized devices. This is because, again, what we're dealing with over here is micron-sized samples, like 5 micrometer wide. So the critical switching current will be pretty large. However, if naively we shrink or let's say the channel size can be scaled down, like for the ideal SOT and RAM, we can shrink the size of the channel to 50 nanometers. And this efficiency will scale correspondingly, then this can go up to, say, 2 microamp inverse. So that will be comparable to the STT and RAM case. So we're currently working on trying to further shrink the size of the device and see if this scaling is correct. And more importantly, besides the typical switching measurements, using this protocol, you can just connect the device and then let the probe station to run overnight or run for several days if your device is robust enough to get this kind of endurance test. So these are the results that we got from the standard tungsten cobalt boron bilayer structure. And we do see this kind of very consistent or very constant switching current, and also very constant delta R's. Although we do see this kind of gradual increase, so let's say gradual decrease, or here over here for the L stage gradual decrease, and for the R stage gradual increase for up to, say, 10 to the 4 cycles. But the resistance, or the delta R, in terms of readout is still pretty robust. So we believe that if we can make the pillar smaller, we probably can make to get endurance test data and also the switching data that will be very close or fairly close to the final SOT 3-terminal device. And for the damping light torque efficiency and field light torque efficiency, like if these numbers are the numbers that you're interested in. Of course, you can use a very simple, like a fitting function over here. For instance, for field like torque, it's directly related to this, the shift of the AMR loop, or this effective field along y direction. So from the slope of H effective versus the current that you apply, you should be able to extract this quantity. And as long as you know the MS, of course, you have to do the VSM measurement to get the saturation magnetization of your sample. And if you know the thickness of your sample, ferromagnetic layer, you can estimate this field like torque efficiency. And more importantly, for the damping like torque efficiency, it's more complicated because what we have from the switching data is only the switching current density, or the JC0 over here. So this is very similar to our early demonstration of current-induced spin-hole torque switching in the nano-sized three-terminal devices. We use this equation to estimate the spin-hole angle, or the damping like torque efficiency. So you need some extra information. For instance, the Dmac field of your ferromagnetic layer, and also the damping constant of your ferromagnetic layer, or your heterostructure. So in order to extract those information, you have to do extra measurement. Over here, we do SDF, spin torque ferromagnetic resonance, or SDFMR, to extract this kind of spectrum under different frequencies. And from that, we can extract the damping constant as a function, let's say as a function of the covalent boron thickness that you have, so such that you can plug in, and also the Dmac field, such that you can plug into this equation and then estimate the damping like torque efficiency. So the bottom line here is that if all you care about, for instance, at ITRI, what they care about is only the switching current density, or switching current, and also the thermal stability, then you don't have to do the extra spin torque FMR measurement. But if you're interested in extracting this value, you have to do some extra works. So that's the trade-off. So here we summarize some of the data that we extracted from the sample with different covalent boron thickness. We can see that there's the SOT efficiency gets larger when the covalent boron thickness is smaller. But the field like torque has this kind of gradual decrease, which is as expected, because when the thickness is thicker, probably this effective field, or the spin hole field, will get smaller. So this is also expected. And also the magnitude of the field like torque efficiency is much smaller than the damping like SOT efficiency. And over here, we do some extra tests with different MGO thickness, because we're wondering if the tunneling barrier thickness will affect the performance of the device. Interestingly, we found almost no thickness dependence in terms of the damping like SOT efficiency, while for field like torque, there's a gradual increase when you increase the MGO thickness up to, let's say, 0.6 or 0.7 nanometers, and then it becomes fairly constant. But again, the field like torque efficiency is much smaller than the damping like torque efficiency. So finally, ITRI, the research facility, provided us some very nice films prepared in their 8-inch fab lines. And the film structure they gave us was this 4 nanometers of tungsten with 1.4 nanometer of covalent boron. And on top of it is 2 nanometers of MgO. And they further annealed this sample at 360 degrees Celsius with an in-plane field applied. The magnitude is about 1 Tesla for, I think, 30 minutes. And interestingly, even for bare films, they found the VSM data is not shown over here, but it has a very clear easy axis along the direction of the field that they apply during this annealing process. So we again pattern these films into micron-sized devices, whole bars, and then we measure the same thing, the longitudinal resistance or the AMR along the x direction. So we first apply magnetic field along the hard axis. So over here, the easy axis is along x direction, and then the magnetic field is applied along y direction. And we do see this kind of hard axis behavior. So the anisotropy field is not that large. It's probably around 500 to 600 Oersted, but it's already very clear, even for this kind of bare thin film, not patterned into devices and not having any shape anisotropy, only by annealing. So by applying positive and negative currents, we don't see very clean shifts in terms of this AMR loops. We do observe this kind of small shifts over here, which corresponds to the UMR or the USMR. And this kind of shift is much easier to be observed if you apply the magnetic field along easy axis, because we will see this kind of sharp switching in terms of the longitudinal resistance or the AMR. So this USMR is probably only about, let's say, 0.9, like 0.9 milliohm. So here I'm using arbitrary units, but I believe that it's around like 1 milliohm. So it's still pretty small. And the signal to noise ratio over here is acceptable, but we're trying to improve that. But at least over here, we can already see this kind of switching. And also, you will see that there's a shift in terms of this hysteresis loop, which corresponds to the spin-hole field that we saw earlier. But over here, because the switching is a purely easy axis behavior, so you can see this kind of shift in the step from the USMR very clearly. And we also do the same thing. So the protocol that we apply, that we employ, is by applying sensing positive and negative currents during one step, and then we subtract, for instance, these two signals to acquire this kind of field sweep hysteresis loop. And over here, we apply currents to do the switching. Again, we can see this kind of reversible current-induced switching loops. And the resistance difference over here is consistent with the resistance difference that we observe over here. So over here, we're still working on more samples from E-tree and to see if we can get a much cleaner results from those films provided from our industrial partners. So our take-home message here is that the characterization of SOT from this bilayer structure with in-plane magnetized ferromagnetic layer is doable, and we can do that in an all-electrical way. And the in-plane current can generate both this in-plane spin-hole field or effective field that will shift the AMR loops. And also at the same time, you will see that the UMR can also be utilized to serve as a means to tell the difference between two different magnetization states in this kind of bilayer devices. And the switching efficiency, if you what you care about is the thermal stability over the switching current or switching current density, it can be estimated by this approach, by changing the pulse width of the current that you apply, or by changing the temperature during the current-induced switching measurements. And both damping light and field light SOT efficiencies can be estimated, and it can be employed to test those industrial level films, especially with those films with easy access. I believe that the switching is actually much cleaner. So our future plans, or actually the ongoing project, is that we're going to work on shorter pulse switching measurements, perhaps down to nanoseconds. And we're going to employ these techniques onto different material systems, for instance, in novel materials like topological insulator, Wassermann metals, and different kinds of semi-metallic systems. And for our collaboration with ITRI, probably the most important thing is that we want to integrate this into automatic testing equipment, or ATE for short. And we look forward that this protocol can be employed onto it, perhaps with better accuracy by changing the DC measurement protocol to an AC approach. If our industrial partner is willing to change their probe station from the DC measurement technique to, for instance, using the lock-in amplifier. And I believe that by using that, we can acquire better signal-to-noise ratio, comparable, even better than the work like published by Dr. Avicii back in 2015. So finally, I want to acknowledge my students, especially Yanting Liu, who was the first author of this physical review applied paper. Unfortunately, he's still trapped in mainland China, and we hope that our team hope he can come back soon to rejoin the team and then continue his PhD study. And also undergraduate students or other PhD students who contributed to the establishment of the probe station, and also the assistance in the thin film preparation. And I also want to acknowledge all the funding agencies, ITRI, TSMC, and also from NTU, and most importantly, from the Ministry of Science and Technology. So here I want to thank you for your attention, and I'll leave the slides here.
All right. Thank you very much for the interesting talk. So this talk is open for questions. If you're in Zoom, please use the raise hand option. I notice some new faces, new names. So if you don't know how to do the raise hand, you can do that by clicking the participants button on the bottom of the screen. And in the pop-up menu, the raise hand option should be on the bottom of that participants list. The first question will be asked by Qiming. Please go ahead with your question.
Hi, Qifeng.
Hi, Qiming.
Hi. Thank you for the very nice talk. Okay, I think this is very important for us to characterize the thin films in a much easier way. I have a question. So you characterize these implant films. They are whole bar device, right? You don't pattern it into pillow.
That's right. That's right.
Okay. So I believe that it is necessary to observe some coercivity first, and then you can talk about all the measurements you are doing. I mean, implant coercivity. You have the AMR.
Yes, that's right. So, so that's the reason why, if we look at the measurement from those films, which was annealed with the implant field, the implant coercivity is actually very obvious. So for this part, I believe that the switching is pretty clean and should be okay. And to answer your question, I believe that your question is about our data over here. So for AMR measurements, we do see some sort of hysteresis over here. But like you mentioned, this is definitely not a single domain switching. So we believe the switching over here is probably only, like say, a part of, or a major part of the domain has been switched. Because if you want to saturate all the domains and having them pointing along the same direction, we have to apply field, let's say, up to 400 Oersted. So all I can say is over here, we have a very, very small coercivity, and we can switch those domains with small coercivity.
Thank you. So yeah, this is actually, I have a lot of questions. So you can see that there's a very nice AMR data, right? So yeah, this is AMR plus unidirectional SMR. Okay. Yeah. So do you always observe this kind of nice AMR in this kind of whole bar device?
Yes, for the tungsten device, it's very obvious. In fact, we started from using AC measurement, and we realized that for tungsten devices, the AC measurement it's probably not necessary. So we switch to DC. But that's not the case for platinum base. For platinum base, as I show over here, you'll see that the USMR per current is actually very small. So even if you apply the DC current to say 6 milliamp, the delta R that you'll see is maybe only 0.01 ohms. So it's actually very small, at least for the DC type of measurement. I think if you use AC, maybe it's larger, but for platinum base, typically we probably need to use AC, use lock-in to see a much cleaner signal.
Okay, thank you. Last question is about the data, the thermal stability and the current, the metric. It's on the page like 13 or this one. So for this particular measurement, I did a calculation. So you actually use the pulse duration from like 50 milliseconds to probably 1 second or even 2 seconds. So
yes, I think probably from 1 second down to maybe 10 milliseconds. I think the shortest, I mean, for this type of measurement, if you're dealing with micron-sized in-plane magnetized samples, I think the shortest pulse that we can see a very clean full switching electrically is probably 1 millisecond. For Hobart, let's say for perpendicular devices or for nanopillar devices, I think it should be much easier to go down to say like a microsecond or even shorter. But for large in-plane magnetized samples, I think it's very hard. It will be very hard. Yeah.
Okay. Thank you.
So that's the reason why I mentioned that over here is a very let's say very like preliminary like proof of concept, and eventually we want to do something like the Hitachi Global Storage people did, make a nanopillar on top of, for instance, a Hobart device, and then use the same technique to probe that.
Okay. So actually, on the right panel, you show the cobalt iron boron thickness dependence. So you show almost a constant like the epsilon, right? So it means that the switching current will increase almost linearly with the cobalt boron thickness. Do I understand correctly?
Yeah, like if you think that the thermal stability, if it's a constant, of course.
Okay, so what is the thermal stability for your for your thin films? Is it thickness dependent?
Actually, I don't have the data here, but maybe I can get back to you when I
sure. Okay,
data.
But
if I remember correctly, I think over here the switching current, let's say, I cannot be very certain right now, but I think the variation for thermal stability is not that huge.
Okay.
Yeah, within this thickness range.
Okay, thank you.
So by the way, for participants on Twitch, if you have questions, you can type your questions in the chat box and I'll read it for you. Next question will be asked by Mahendra. Please unmute and go ahead with the question.
Hi, Professor Pai. Great talk.
Yeah.
I have a question. For the in-plane magnetization switching, there is effect of the worsted field also. I was if you have estimated worsted field in generated by the current in these tungsten and platinum-based devices.
Yeah. I don't have the data here, but I can show you that for the tungsten-based devices, we checked that. First of all, the worsted field will be pointing along the opposite direction. I think that's typical for our tantalum and tungsten-based devices. And for 4 milliamp, the worsted field, I think, will be pretty small. I'm not so certain about the magnitudes right now. But for the platinum case, indeed, for the platinum case, so we apply the current up to say 7 milliamp or sometimes close to 10 milliamp. That is already close to the coercivity of the cobalt iron boron layer, judged by the AMR loop, the coercivity that we measure from the AMR loop, from those platinum covalent boron devices. So it is possible that in the platinum-based devices, the Oersted field might play an important role, or at least assisting the switching. But for the tungsten case, I think it's much smaller than the damping like torque effect.
I see. Another question is, you have annealed tungsten sample up to 360 degrees C.
Yes.
Have you annealed tungsten or platinum, cobalt iron, boron bilayers up to 400 degrees C?
You mean the same structure and then above 400?
Right, yes, or similar structure with cobalt iron boron as a ferromagnetic layer?
We haven't tried that yet. I mean, I think the film was prepared by E3. I believe that they've tried many different types of recipes. And I believe that they might have some tricks or some recipes that allows them to anneal those samples up to 400 or even higher, because I believe that's what all the people are trying to overcome, to make sure that the device can survive such high temperature annealing. But the films that they gave us, they have different annealing temperatures. The 360 was the highest that they gave us.
Thank you. Yeah.
Mm-hmm.
All right, Minghai, please go ahead with your question.
Hi, Shifang.
Hi,
hi. So thanks for the great talk. I have a question about your estimation of the switching efficiency using, I think, like current switching in your hall bar. How is this different from, let's say, I just DC sweep the current through the hall bar and get the switching current? I mean, in a very rudimentary way, like sweeping the current back and forth. So how is your method different from that?
I'm not so sure what you mean by back and forth.
That means let's say I can have a hall bar, then I can sweep the current from negative to positive and back to negative. Then I can observe the switching loop. Yeah. Then if I extract the switching current from that and I do the fitting, then I will get pretty much the switching efficiency. So how is that compared to your method? Is that the same or
yeah, I mean, this is exactly the same, because we extract these switching from the current-induced switching loops over here. So yeah, so the switching current that you saw in the next slide was extracted from a lot of this kind of switching loops with different pulse widths.
I see.
So over here, like each pair of data corresponds to the current-induced switching data from a specific pulse width.
Okay, I see. Thank you.
Yeah.
Shane has a question. Do you want to just go ahead and directly ask the speaker? Or I can read it for you. So Shane just asked, does the annealing temperature have an influence on the strength of the torque?
We're not so sure yet, because there are not that many samples that they gave us. E3 was, TSMC was a spin-off from E3, and they might have some collaborations with them as well. So the samples that can share with us is very limited. And so what we propose to them is that if you can give us a sample with nice in-plane anisotropy, then we can probably see a better result. And apparently they can provide us this very nice film, because in the past I don't really think that the bare film can have this very clean, like easy axis and hard axis behavior. And so apparently this is what they achieved. And I believe that if they use a lower annealing temperature, maybe the anisotropy is not that good. So that's the reason why they gave us this probably the most, let's say, the optimized one. Yeah, so unfortunately we don't have the data for the efficiency on the different for different annealing temperatures.
Yeah, thank you. Is there any other question? There's a question from Wang. What about the role of interfacial DMI between tungsten and cobalt iron boron contribution to switching?
So unfortunately, over here, well, we're not able to quantify or to estimate DMI. So DMI, or at least the discussion of DMI started when I believe back in 2014 or 2013, when people started looking into the domain wall motion in those perpendicularly magnetized samples patterned into nanowires. And for the in-plane case, especially for the switching measurements, is not that frequently discussed. So it's also probably not, I'm not sure if there's any possible approach to use the switching data to quantify DMI. And I'm not so sure how much the DMI will affect our switching. So at least for this in-plane switching case, we haven't really considered any contribution or any effects from the DMI.
Thank you. Li Jun, you have a question? Please go ahead, unmute yourself.
Hi, Jason.
Mm-hmm. Hey, Li Jun.
I have two questions. One is from the pulse weights measurement, you determine the same stability delta. Mm-hmm. What is the physics of this same stability? Like, what determines this same stability in thin films?
Mm-hmm. So the thermal stability here, maybe as Qiming just asked earlier, and that I mentioned that the switching is actually maybe just a part of the ferromagnetic layer, because we were dealing with a very large pattern film. So all I can say is a part of the ferromagnetic layer has been switched. I'm not sure if it's full switching because we haven't really done any longitudinal mode measurement. But judging from the AMR, like say the resistance difference, is probably not a full switching.
No, I mean, you know, in PLS you have either in PMA or you have shape anisotropy that can determine this delta value. But in a thin film, what determines this delta is like a non-uniform anisotropy or what?
Yeah, so we believe that maybe like at least in the domain that has been switched, maybe there's some magnetocrystalline anisotropy. But that's for just the domain that's been switched. So we're not unable to see or to probe, like say, the thermal stability of the whole ferromagnetic layer. So even now we're not so sure. For instance, the thermal stability maybe is really can be calculated by using like the anisotropy, energy constant times the volume, but we're not so sure what KU that we're referring to. Maybe it's the magnetocrystalline anisotropy, or locally there are some shape anisotropy, but from AMR measurement, we don't see any shape anisotropy at all, at least in those samples prepared by ourselves.
I see.
Yeah.
Okay.
Yeah, for the films prepared by E3, because it has a much like a cleaner, let's say cleaner hard axis behavior, such that we can estimate the anisotropy field. From those films, we can estimate KU times, for instance, a specific like a subvolume or the activated, thermally activated region, and that product can give us maybe a more reasonable estimation of the thermal stability. But over here, all I can say is we can extract a number but we're not so sure what this number corresponds to. So that's again back to what I just mentioned. We want to make smaller size, a pattern like ferromagnetic layers, such that we can have a better understanding of what's going on.
I see. Yeah, thank you. So the second question is, as you mentioned, this measurement corresponds to a small portion of the domains that are switched, right? Then in the calculation of spin torque efficiencies, you use the macro spin model, which means you use the thickness and M effective of the whole thin film. That has any influence on the estimation?
Yeah, that's true. So the estimation should be pretty rough because over here, like I said earlier, the thermal stability might correspond to a certain volume of the ferromagnetic layer on this pattern film. Right. But the switching current that we the switching current IC0 that we extracted is actually flowing through the whole device. So there might be some discrepancy. So I'm not so sure like if it's an overestimation or underestimation at this point, because both things will have large, at least the delta will have a very large geometrical, let's say contribution. Like depending on how large the volume has been switched, this will be affected by a lot. So this is only a very, very rough estimation. Actually, the referee doesn't like, I think most of the referees don't like this part. So eventually, we say that the scaling is not going to, we remove this part in our paper. So this is only a very rough estimation. We just want to show that this is possible to do this kind of measure.
Yeah. Also, you have a slide for calculation of the damping torque and feel like torque 1.
Do you remember which?
Like this page. Yeah. So like on the second equation, like you use you have a thickness of ferromagnetic layer and the damping and M effective. They're all for the assumes a very uniform thin film. So
so this is based on the macro.
Right. So there's some details. Yeah. Okay. Thank you.
Okay. I have there's I think it's a question from Suriram. And he has 2 parts of his question. I'm going to just read it to you. The first one is, what is the magnitude order that you have calculated from this method? I think that's the magnitude of the spin-orbit torque.
The magnitude of the spin-orbit torque?
Or maybe you can just comment on the equivalent field. How large is the equivalent field due to the spin-orbit torque used in your experiment?
Field? Actually, I'm not so sure how large the field is, but all I can say from all the in-plane and perpendicular samples that we tested in our labs, typically in a sample that is about 5 micrometer wide, by applying 1 milliamp of current, we will get maybe 10 to 20 oersted of effective field from the damping light torque. So that's this is a huge range because it depends on like the thickness of the ferromagnetic layer that you have, and also like the anisotropy is in plane or out of plane, but typically it's like 10 to 20 oersted per milliamp. And again, this is by confining the size of the device or the channel to 5 micrometer, because this is our standard like whole bar pattern. If you use different width of the device, then you'll get different number. So you can probably calculate the current density per current density number by yourself.
Yeah. Thank you. And the second part of his question is, can you comment on the damping field values by measured by other methods? Have you compared with other same sample measured with other methods?
I see. At least for the in-plane case, over here, we haven't tried different types of measurement because, of course, we can do a Spintor FMR. Spintor FMR will give us a number that is fairly close to what we have shown over here. For instance, these tungsten cobalt-boron samples, like I mentioned earlier, in order to extract these damping constant and DMAC field, we did perform STFMR. And for STFMR alone, we can already extract, the damping light torr and field light torr efficiency. They are quite comparable to what we show over here. But we haven't tried other more common methods. For instance, I believe that Masa Hayashi proposed the in-plane harmonic measurement before, and also Professor Xinfan proposed also the effective field methods before, or using MOC to characterize the effective fields. But we haven't tried that. So all we did over here is the STFMR and also the switching measurement. Yeah.
Thank you very much. Do you have other questions? Just a quick check. Okay, if there's no other question, I want to thank Chi Feng again for the very interesting talk and in-depth explanation.